Today we begin Chapter 3, Exponential and Logarithmic and Logistic Functions. That's what the whole chapter is about, exponential, logistic, and logarithmic functions. Today, and tomorrow, but today we're going to be working on exponential functions only. Today's exponential only. Have no fear, I am the king of logarithms. I know Ian came in and said he's so bad at them. I got your back, don't worry. I am the best logarithm teacher on campus. Telling you I am. But today we'll do exponentials, okay? We're going to start with the parent exponential function, a bunch of its properties, and a little bit of vocabulary, I guess. So it says, let A and B be real number constants. Okay, so A and B are not variables, they're numbers of some sort. An exponential function of x is a function that can be written in this format, a times b to the x. A is often known as the initial value, or like principal when you're doing real-world problems. B is called the base. B for, but what is that noise?
Mr. McCutcheon, you're not sharing.
I'm not sharing. Of course I'm not sharing. Because I'm recording these notes, I forgot to share. I mean, it's just, yeah, I'm recording. Yeah, it's just one of those things I do, you know. Just demonstrate that I don't know how to do my job. No big deal. It's no big deal. It's just, you know, what I get paid to do. Here you go. Try this again. Thank goodness one of them said something, right? Anyway, luckily I hadn't really written anything yet. Cool, there, now we're on it. So a, b to the x. So a is known as your initial value, b is your exponential base. A couple rules here. A, the number in front, must be positive. Exponential base must be positive. And the exponential base cannot be 1. Because if it was 1, it wouldn't matter what number you plugged in for x. You would always just get a 1 back, right? Because 1 raised to anything is always going to be 1. So a and b must be positive numbers, and b is not allowed to be 1. Great. B is base. These are properties that are true for all exponential growth or decay functions, not exponential functions in general, specifically exponential growth and decay functions. The domain is going to be all real numbers. Now that's because you can raise a value to any number you want to. You'll always get a number back. But your range is restricted. Your range is going to go from 0, not including 0, up to infinity. And that is true for the exponential growth function on the left and the exponential decay function on the right. The x-axis, y equals 0, your horizontal asymptote. Get really close to it. Not going to touch it. The continuity says all real numbers. That just means that this thing has no asymptotes, no vertical asymptotes, no holes, things like that. No points of discontinuity, no symmetry. They're both bounded below because they do have a horizontal asymptote. No extrema. And even though they both get really steep, they are not approaching a vertical asymptote. They will forever grow to the right or fall to the left and grow to the, no, rise to the left. There we go, I said it right. I said it backwards. The point is, no vertical asymptote. There. Okay. So the one on the left is exponential growth. How would you recognize exponential growth? The base would be any number bigger than 1. That's pretty important. So how do you recognize exponential decay? The base is any number between 0 and 1. Can't say less than 1 because that would imply negatives, and the base must be positive. So as long as the base is bigger than 1, growth. Base between 0 and 1, decay. There you go. Mr. Emmett says that a can't be a negative number. Why not? Well, I mean, a could be a negative number, but it wouldn't be classified as exponential growth or decay any longer. At that point, you just have some exponential function. I could shift them up and down. That would change the horizontal asymptote. Okay. Now it's just some exponential function. It's no longer growth nor decay. It's just some function. I'm not going to worry about the big dots they have on there. I'll get to those. I have a system for those, so let's not worry about those for right now. Exponential growth, always increasing. Exponential decay, always decreasing. We have a limit notation for our endings. It just says that as you go to the right, growth goes up. As you go to the left, growth approaches 0. And for decay, as you go to the right, you approach 0, but as you go to the left, you shoot up to infinity. That's it. Oh, and the base, the number, if it's growth, is called the growth factor. If it's decay, it's called the decay factor. Now we can actually start doing some stuff. For these examples, we're literally just going to plug in these numbers. Just plug them in, that's it. And we don't need a calculator to do this for the first 3 of them. We will need a calculator to do the last 2 just to get the decimal answer. And you would only really want to do that if you were trying to graph these things. And that's the only reason why we're even doing this is in case you had to graph one, could you plug the numbers in and get y values? Let's see. What is f of 4? 2 to the 4th power. That's just 16. Easy peasy. How about f of 0? Yeah, 2 to the 0, 1. Good. The 2 pictures that we had up above, they both had a y-intercept at 0, a. Well, you just saw that happen. When you plug in x equals 0, your exponential base raised to 0 automatically equals 1. And then whatever the a value is, here that a value is 1, that is going to be your y-intercept. Awesome. See, -3, f of -3. It is 2 to the -3. Remember, anything with a negative exponent just means it's on the other side of its fraction bar. So this is actually going to be 1 over 2 to the 3rd, which is 1/8. That's 0.125 if you wanted to have it as a decimal. There you go, 0.125. F of 1/2. 2 raised to the 1/2 power. Let me remind you that a 1/2 power is actually the square root. So this is actually the square root of 2. It's about 1.414. So you'd grab a calculator and see what the square root of 2 is. There you go, 1.414. And then lastly, -3/2. I'm going to scoot over to the right. F of -3/2. 2 raised to the -3/2. Goodness. Well, just a second ago we saw a negative exponent flip this thing over, right? So it's going to be 1 over 2 to the 3/2. We just saw the 1/2 power was actually a square root. So I have 1 over the square root of 2 to the 3rd. That's 1 over √8. I'm not even going to pretend to know what that number is. Instead, I'm going to look at my notes where I have the answer written down. 0.354. And I would expect you to do the same. Grab a calculator. So everybody can evaluate exponential expressions easy enough. Plug a number in. Type it on a calculator if it's ugly. Not too scary, right? Not too bad? We're good? I just realized I stepped off camera for my zoomies. All right. Can I move without anybody panicking? Okay. I'm waiting for it. There we go. So what we got going on? Here, I have a table of values. This table of values is representing x, y's for the functions g of x and h of x. Our job is to find the exponential equation for g of x and h of x. It's actually pretty easy to do. It's actually pretty easy. We know that they're both going to be of the form y equals a b to the x. We have 2 jobs: figure out the base and figure out the initial value. Initial value is always found when x equals what? 0, yeah. So if we look over at x, oh, look, check it out right here. Look, there's our initial values right there. But I am going to show you why it's true. I'm going to show you why it's true. So let's say g of 0 equals 4, right? Yeah. So 4 equals a b to the 0. And that's how you get, oh, okay, a equals 4 because b to the 0 is 1. That's why it's working. And the same thing would happen for h of 0. We'd say 8 equals a times b to the 0. B to the 0 is 1. Oh, a is 8. So far, we have that g of x is equal to 4 times the base raised to x, and h of x is 8 times b to the x. That's what we have so far. Simply because our initial values are going to occur when x equals 0. So that was handed to us. How do we find the base, though? The base is going to be the number that's getting different exponents each time, right? So that number would be to the first, and then to the second, and then to the third, and then to the fourth, which means from each term, you would have another times b. So first I'd have a, then I have a times b, then a times b times b, then a times b times b times b, so on and so forth. Literally going from one term to the next means you multiplied by b. So all you have to do is go to your table, pick one place, it doesn't matter, and see what are you multiplying by as x gets bigger? 3. Oh, okay, there you go. Base is 3. So for g of x, it is 4 times 3 to the x. That easy. And you want to do the same thing for h. You just go anywhere where you can easily see what you're doing. What did I multiply by to get from 8 to 2? 1/4. There's your exponential base. Ta-da! That easy. Finished. Big table there for no reason. Needed very little of it. Yes? Hmm? Oh, no, you can't. You can't multiply a and b because b has an exponent. So if you were following the order of operations, the exponent would have to happen first. And since we can't, because exponent is an x, it'll always be 4 times 3 to the x. All right, so these three are transformation style questions. There are some transformations that can be performed on the exponential growth and decay functions, and you still have exponential growth and decay functions without breaking the rules. Let me tell you ones that you can't have. You can't reflect over the x-axis, because if the curve is below the x-axis, how would you call that growth or decay? Can't do that. And you also are not allowed to shift them up or down. And then, I mean, you can shift the graph, but it would not be called an exponential growth or decay function anymore. In order for it to be classified as a growth or decay function, still, you cannot shift up or down. The horizontal asymptote must be the x-axis. You guys cool with that idea? So no shifting up and down. That breaks the rules of growth or decay. And no reflecting over the x-axis. That breaks the rules of growth or decay. But all the other transformations, they're still game. So this first one, your job from here on out is to think, because remember when I did high velocity, guys, is to think that the inside is wherever the x's are. So, bloop, parentheses right there. That's where the x's are. Do you need parentheses? No. I only wrote them so I could talk about the inside. Horizontal, inside, opposite. X minus 1 is what transformation on the original? Shift right 1 unit. We're supposed to sketch this graph by hand. Okay. Oh, let me make this smaller. Making this too large for no reason. Come on, active panel. Here we go. Now I told you the 2 dots that were on the pictures that I kind of had my own little ways of doing this. I do. And here's how this works. Things are easy to graph when you make the exponent equal 0. And things are easy to graph when you make the exponent equal 1 or negative 1. Those are the only 2 coordinates that you're going to require. And the third object you need is the horizontal asymptote. Well, I mean, since we're talking growth and decay functions, the horizontal asymptote is automatically the x-axis. You need two things. What makes exponent equal 0? And the other x you need is what makes the exponent either 1 or negative 1. And it's not like you need to memorize this, but when it's growth, it's just easier to make the exponent equal 1. It's easy. And when it's decay, it's easier to make the exponent equal negative 1. It's just easier. Why, Mr. M? Because if you go the other direction, you end up with very small numbers, and those are hard to plot. That's why. So for us, when our exponent is x minus 1, what x value is going to make the exponent equal 0? X equals 1. That's the first thing that you are going to evaluate. So let's see, x equals 1. G of 1 then is 2 to the 0, which is 1. Oh, we have a coordinate at 1, comma 1. Cool. And what x value is going to make, is this growth or decay? Well, the exponential base is bigger than 1, so it's set up as a growth, right? What value for x is going to make the exponent equal 1? 2. So if I plug in x equals 2, I get 2 to the first, which is 2. So x equals 2, y equals 2. It looks linear, but it's not. We all know it's not. We get this. There it is. Ta-da! So easy, right? No. We could do negative 1 if you want to, but you don't need to. You only need 2 points to see the shape. And the reason why I chose to make the exponent equal positive 1 is because it's growth. Okay? Yeah, you can if you want to. If you wanted it to be negative 1, you'd have to plug in x equals 0, and then you have 2 to the negative 1, which is 1/2. So you have 0, comma 1/2 is the y-intercept, if you wanted to, but it's not necessary. And it's not always pretty either. Next one looks like growth, doesn't it? Because it looks like the exponential base is greater than 1. Tell me, my x is now negative x. What kind of transformation is that? Over the y-axis. Yeah, this is reflect over the y-axis. Now, wait a second. Reflect over y-axis. Let's just look at this orange curve for a second, because that is growth. If I reflected it over the y-axis, what would it look like? The orange curve, it would look like a decay graph. 2 to the negative x is decay. You know why? Because anything raised to the negative exponent just goes to the other side of the fraction bar, and it becomes positive. I could say 1 over 2 to the x, but this is equal to that. It's the same thing. So yeah, it's a decay function. So we got a decay function by reflecting over the y-axis. Let me be really clear here. Changing the exponential base to another number is, through ridiculous trickery of mathematics, you can show that it's a transformation, but you don't want to see it, okay? So we're going to stick with the classic transformations that we learned in Algebra 2 and practiced earlier this year. First thing I want to do is figure out what x value would make the exponent equal 0. 0. So what is h of 0? It is 1/2 to the 0, which is just 1. Oh, 0, comma 1. Cool. Oh, horizontal asymptote. Duh. There you go. Y-intercept. And then you ask yourself, Do I want this exponent to be 1 or -1? Well, it really doesn't matter. But since it's decay, I think it would be easier to go with what makes the exponent equal -1. And if you look at it as 1/2 raised to the x, what x value do I want to plug in? Crickets. Okay, let's try it again. Since this is decay, if you want the exponent to be -1, what x are you going to plug in? You want the exponent to be -1, so what exponent, what are you going to plug in? -1. Good gravy. What is 1/2 raised to the -1 power? It's 2. That's why I raised it to a negative exponent. I wanted a pretty value that wasn't an ugly decimal. So we have a number at -1 comma +2. You're not understanding why that's working? Fine. Just plug in whatever you got to plug in to make x equal 1 and -1. It doesn't matter. Your job is just to see the shape. Just see the shape. And the last one. We're taking our 2 to the x and we're slapping a 3 on the front of it. What kind of transformation is that? Yeah, vertical stretch. Factor 3. Vertical stretch factor 3. Well, because it's a growth function, I'm just going to go with what makes the exponent equal 0 and what makes the exponent equal 1. What makes the exponent equal 0? Yeah, 0. So when you plug in 0 to k of x, you get 3 times 2 to the 0, which is 3 times 1. It's 3. So 0 comma 3. I should probably put a 3 on there, scale purposes. I should probably put a horizontal asymptote on there. And again, because it's growth, I'm going to make the exponent equal 1 by plugging in a 1. That k is a little sideways. 3 times 2 to the 1, 6. That's just 3 times 2, 6. And growth. There you go. You know, these kinds of curves are just way too easy. And our authors just flat did not care about difficult exponential growth, decay, or just exponential function graphing in general. So because of that, I will have to supplement this material later in the week to learn how to graph tough things. Do we have any questions on transformation / sketching graphs? Easy, right? Easy, easy, easy. Now we get to talk about the number e. That's right, I said what you heard. The number e. Yes, e is a number. It stands for Euler's number. And e is irrational, like pi or like square root 2. We have to use a symbol to represent it because the number itself has no pattern, never comes to an end. It has a value of somewhere around 2.712. It keeps going, but 2.712-ish, okay? It's a number between 2 and 3. We did not make this number up. We found this number. It was not made up. It's discovered. Discovered in more than one way. My favorite way is this. So on and so forth forever. And if you keep doing that, eventually you will get e. That's one way of doing it. And the other way of doing it, I believe, is set up like this. The limit as n approaches infinity of 1 plus 1 over n raised to the n. I think that's also it. I think. Either way, if you work these things out to all infinity, you crash into the number e. E is known as the natural exponential base. And since it is a number, we can use it as an exponential base. That means we can graph e to the x, which you did in Algebra 2 Honors. Notice we're taking our a times b to the x and we're replacing it with a times e to the kx. Whoa, 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 there's a new letter. I introduced a k. But why? Well, here's the thing. If you didn't introduce k, since e is a number bigger than 1, every e graph would be growth. But we can also represent decay with e. So we have to throw in that extra variable of k. K determines whether or not this thing will be growth or decay. It's weird saying k and decay. But anyway, the k value determines growth or decay. Positive k value, growth. Negative k value, decay. Why, Mr. Crab? Because it can be thought of as saying this. That's why. You see, if k is positive, you have an exponential base that's bigger than 1. But if k is negative, you have 1 over e to some power, which is an exponential base that's between 0 and 1 every single time. And that's why it's decay. So that's up to you to see. Basically, e with the negative exponent, decay, e with a positive exponent, growth. And that k value would be known as the growth factor or decay factor, I believe. No, maybe not. That's only when you're talking about b. It doesn't work for k as well. Oh well. Come on, board. You can do it, computer. Come on. Come on. Oh, look, we're crashing, everybody. Yay. There we go. Got it. I got it. It's not me. That one's not me. That's the computer. It doesn't have the brain power to stream and record at the same time. It's probably a processor or a graphics problem, if I had to guess. Because the CTE computers can handle what I'm doing. They don't struggle. The ones that we do all the 3D animation and stuff on campus, they could do this, no issue. I think it's the graphics processor. So this is the same basic 3 questions, except they're E instead of some other base. But I think that the process still works the same. Yeah. Yes, if the k value is not there explicitly, it's a 1. Yeah, so like for part B, k is -1. And for part C, k is just 1, like you said. All right. You guys, so remember, we're calling the place where the x is the inside. You don't have to put parentheses on it. I'm just doing it so you can call it the inside. Do you guys remember what multiplying by 2 on the inside is as a transformation? Yeah, it's 1/2 because inside opposite. So this is a horizontal shrink factor 1/2. That just means this thing is not going to be as wide. Still have the same horizontal asymptote, just like that. And the process still works the same. What makes the exponent equal 0? What makes the exponent equal 1? I mean, it's just easier. What makes this exponent equal 0? Yeah, 0. Yeah. You drop a 0 in there, you get g of 0 is e to the 0. Oh, it's 1. Okay, this one crosses the y-axis at +1. And then you ask yourself, what would make the exponent equal 1? Ah, 1/2. Yeah, so we get g of 1/2 is e to the 1, which is about 2.712-ish. Almost 3, right? So here's 1, here's 1/2, here's 3, and we're just darn close to 3, aren't we? Right about here-ish. That looks good enough. Make a nice fat dot. Won't be able to tell exactly where it is. Who's to say I'm wrong? There you go. Part B has the exact same transformation that Part B had on the other page. So I don't think it's a shock to anyone when I say that that is a reflection of the y-axis. I want the exponent to be 0, so I'm going to have to plug in a 0. And I'd like the exponent to be 1. So what am I going to plug in? -1 this time. Yeah, no, I already said that. You weren't listening. Never was a more true thing muttered. So I want my exponent to be 0, so that's going to happen when x is 0. I said it before you. That's e to the 0, which is just 1. So we're still crossing the y-axis at +1. And I would like my exponent to be +1. The only way that happens is if I plug in a -1. That's going to give me e to the first, which again is almost 3. 2.712 when x is -1. Almost 3. Nice big dot, so no one can argue with us. There it is. And then lastly, sticking 3 on the front of this guy, still, like it was in the last one, vertical stretch, factor 3. That's not different. I love transformations, they never change. Vertical stretch, factor 3. Too lazy to write all the words. Again, exponent equal to 0, exponent equal to 1. Nine tick marks on there because I already know what's going to happen. Exponent equals 0 happens when x is 0. Whoops. I forgot the 3. Hold on. When the board catches up with me, I'm going to put a 3 in front of that e. Yes, oh yes, I am. You watch. You watch. Just you watch. It's coming. See? Told you. There we go. 0, 3 is our y-intercept. I should probably put a horizontal asymptote on here somewhere. There you are. And exponent equals 1 is a pretty easy one to evaluate with a calculator. This is 3 times e to the first, which is just 3 times e. Yikes. 3 times e. So on your graphing calculator, in case you don't know where it is, the e to the x command is on the left-hand side, 3 buttons from the bottom. It's not its own key. It shares the ln function. So in order to make the ln key be e to the x, you have to use the second button. So you would press 3 times second ln, put a 1 as the exponent, and hit enter. And you get 8 and change? 8.16-ish. I thought you said 155. Oh, it's actually 154? Oh, okay. Nah, crap happens. 155. Yep. I believe you. Did it all in your head. Me too. And we're here-ish. Again, make the dot fat enough and no one will be able to argue with you. There it is. That is where these notes are going to come to a close today. So basically, we are saving the logistic functions for tomorrow. You have the ability to do all of your homework except for these 2 questions. So it's only 2 questions that require the back half of the notes. And we will do those tomorrow.